Hey, hello everyone. Welcome back to our AI channel. Uh, let's get back into our AI journey. Today we are entering an exciting area called local search algorithms. Okay, local search algorithms. And in this, what I'm going to tell you is one second. Local search algorithms. These are really very powerful when the path to the goal does not matter. Uh, are you getting what I'm trying to say? When the path to the goal does not matter, but only the solution itself does. Think of them as direct optimization tools. Okay, let's dive in. Like, for example, let's say this is point A and this is point B. We have this, this, and we have this. Okay, like we have these three paths from point A to point B. What I'm trying to say is the this is our end goal, right? This is our goal. So what I'm trying to tell you is the paths like from A to from to B, whatever the path it may take. It may take from a straight line or this curved path or this curved path. It doesn't matter. What matters is did it reach the end? Did it reach the end goal? That's what matters here. Okay. The algorithm name is local search algorithm. You can see here like what exactly are local search algorithms. Okay. Well, unlike systematic search algorithms uh, like we have BFS, right? BFS and systematic search algorithm and depth first searches and systematic. These are systematic. Okay, these are systematic. These are systematic search algorithms. Here, we only work with single current node and its neighbors. Like for example, this is the node uh, we got into. Like if we are here, uh, what we look at, okay, our current node. We look at our current, and then what we look for is just our neighboring nodes. What if if this has some neighbors, then we just only look for our neighboring nodes. Okay, these are systematic searches. Okay, systematic search algorithms. We only work with single connect node and its neighbors. That's it. We don't keep track of entire path, like from in which path we have traveled. We don't go. Okay. Uh, these are local search algorithms. Uh, what is the big advantage regarding this? Okay, they use very little memory. Memory is memory little. They use very little memory. Often just a constant amount, like every time, like when an LSA runs, the memory used is a constant. Okay, most of the times it's a constant, it doesn't dynamically change. Okay, and that too a little amount. They work well even in very large or even infinite spaces. Okay, like for example, let's take our solar system. There are infinite number of stars, and we need to find the distance between one star to another star, or we need to trace a path from one star to another star via some stars or something, whatever it may be. Okay, what I'm trying to say is the solar system is not small; it's absolutely big. Okay, but using LSA, we can go through it. Okay, we can travel from path A to path B even if it's has infinite number of paths, we can trace the path, okay, using an LSA. Um, Here, let's just say in LSA we can trace the path, but let's just say if you go through BFS or DFS, okay, how much time does it gonna take from going from point A to point B? There are infinite number of stars, okay. Sorry guys for the inconvenience. Someone has called me, so I had to go. Um, okay. What I'm trying, where are we? What are we trying to? Yeah. So, um, if the like the space is infinite, then our systematic search would fail, and they're extremely useful in optimization problems where the task is simply find the best state according to some objective function. Okay. uh, so remember, LSS are not about how you go there, but whether you end up in the best possible spot. Okay, it's about LSS. And we have set space landscape, like imagine imagine the set space as a landscape. Here we have objective function, okay, and here we have state space. Look at this graph, like look at this graph. Here this straight this straight line is called a shoulder. Okay, the highest is, it is global maximum, and this is our current state, right? Like we need to look at this, so then that will become our local maximum. And here we have a flat local maximum flat. Okay, we'll get to it. Okay, don't worry if you didn't understand it. Like what I'm trying to say is, the horizontal axis represents different possible states. The vertical axis represents either cost or objective value. If elevation corresponds to cost, our goal is to find the lowest value or the global minimum. If elevation corresponds to objective function, our goal is to find highest peak or global maximum. Local search algorithms explore this landscape. Now keep in mind, a complete local search algorithm will always find a goal if one exists. An optimal one will find the global maximum or minimum. This is the institution behind hill climbing, which we will explore next. Okay, see, we came here with hill climbing search. Okay, let's talk about one of the most famous local search methods, hill climbing. The idea is simple, very simple. Always move in the direction of increasing value, like climbing uphill. Keep doing this until you reach a peak where none of your neighbors is higher. This is why it's also called steep set ascent. Okay, like because we are just going up, we are not going down. We go up till none of your neighbors are higher than the point where you are. Okay, that's why it is called as steep set ascent. But notice something, hill climbing doesn't look ahead beyond immediate neighbors. Like it is greedy local sets, always grabbing the best immediate move. And often greedy strategies work surprisingly well. They make quick progress, but as we will see, they also have pitfalls. Like okay, um, here we have function hill climbing problem returns a state that is local maximum. Current, make note, initial state, loop do neighbor highest value successor of current row. If neighbor value is less than or equal to current value, then return current state, current neighbor. Here, what is the what you are looking here is search algorithm. At each step, the current is replaced by the best neighbor, which means the neighbor with the highest value. Okay, hill climbing gets stuck due to the following reasons. Okay, so what can go wrong with hill climbing? There are three big problems. Local maximum. This is the peak higher than its neighbor, but still lower than the true global maximum. Once you are stuck there, the algorithm has nowhere to go. Okay, what is local maximum? This is the peak, okay, higher than its neighbors but still lower than the true global maximum. Once you are stuck there, the algorithm has nowhere to go. Okay, see, let's say here is global maximum, but before that uh, okay, here These are your neighbors. You came here, you saw this, you went there, you you stand there, your neighbors are lower, but this is the maximum which you are able to see, and you think this is the main maximum, but the global maximum is here, which you can't reach there because your neighbors are still smaller than you. Okay, this is the one of the pitfall. And another are ridges. Okay, imagine a long ridge made up of many small peaks. Moving uphill in one direction might force it downhill in another, making it tricky for greedy sets. Okay, let's do like this. There are ridges, and like this. See, this doesn't mean you are going to a higher place. It's just one of the ridge. Like here is the maximum, but due to the small ridges, you think this is the highest peak point. Okay, Platex. Platex is a flat region of a landscape. Okay, the algorithm keeps wandering around without making real progress. It goes here, 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 and see, it just keeps on going from here and here and here and here and here. It doesn't make any real value. Okay, it just keep on wandering there, and it's another pitfall. Okay, the pitfalls are local maximum, ridges, and plateaus. Okay, and see what we have here, illustration of why ridges cause difficulty for hill climbing. There are the sequence of local maxima here. This they are explaining what we have. Okay, because like ridges are problematic because every move seems to go downhill. The agent cannot figure out the subtle zigzag paths that would take higher. This is exactly why plain hill climbing fails in many practical problems. Okay, variations of hill climbing algorithm. Okay, to overcome these challenges, several variations exist. One is stochastic hill climbing, first choice hill climbing, random restart hill climbing. Stochastic hill climbing, instead of always choosing the steepest uphill move, it randomly chooses among the uphill moves. The probability can depend on the steepness. It's slower but sometimes finds better solutions. We have first choice uphill. The practical variant of stochastic generates successors randomly until you find one that's better, very useful when each state has thousands of successors. And third one, random restart, like conducts a series of hill climbing searches from randomly generated initial. Like here, we restart hill climbing multiples and random initial sets. If each run has a successful probability of P, P1, the expected number of restarts is 1 by P. Okay. If the probability of success P, then expected number of restarts is 1 by P. This is powerful because even if the landscape has many local maxima, a fresh start gives you another chance to escape. So by adding randomness and restarts, we make hill climbing much more robust. Okay. Stochastic sets techniques. Like beyond hill climbing, we also have a wider family called stochastic sets techniques. These bring in randomness as a core component. They don't guarantee exact solutions, but they are often powerful in huge complex set spaces. And this takes us towards algorithms like simulated annealing and genetic algorithms, which we will see in upcoming lessons. Okay, upcoming lectures. Like we have genetic algorithms. Okay. For genetic algorithms, like we have based on principle of genetic recombination and survival of the fittest with a little mutation, proposed by John Holland. It is an robust algorithm to evolve better organisms. It is an optimization algorithm which differs from the standard methods of the following ways. Works with the encoding of parameters. Like I have reference on textbooks here. Genetic algorithms, insights, optimization and machine learning by David E. Goldberg. Try to read this book. Okay. If you want, I will also add the description of this book to in the link. You will find the link of this book in the description. Okay. Benefits of genetic algorithms are they're very easy to understand, and they're modular, separate from applications, and supports multiple objective optimization. And this is also good for noise environments. Always an answer gets better with time. Inherently parallel, easily distributed. Okay, many ways to speed up and improve genetic algorithm based application as knowledge of problem domain is gained. As we gain the knowledge, the answer will be also increases. Easy to explore previous or alternative solutions, flexible building blocks for hybrid software and range of use. Okay, these are when to use the generic code. This is not much important, but just for our sake. Okay, and this is the algorithm. Okay, try to take a note of it. Yeah. Thank you guys. I have completed the episode 12, and in the coming episodes I will come up with something more, and we will continue this topic, or I will get to you another topics. And you can also try to watch another videos, like another series which I am simultaneously teaching here. Like you can go through this and you can go through those videos also. Yeah, that's it, and don't forget to like and subscribe to my channel. And if you have any doubts, just don't forget to uh, put a comment under it, ask questions. Okay, you can contact me, just feel free to do so. Okay, thank you guys, bye bye.